Hello, my precious friends. I really hope that you are doing great. Welcome to today's class. It is our first lesson on the seventh topic of Form 4, which is called cathode rays and cathode ray tube. As usual, let me commence by giving the quote of the day, which states that you will never realize how strong you are until being strong is the only choice you have. We shall discuss that quote at the end of our class today. So today I'm looking at the cathode rays and the cathode ray tube, usually abbreviated as a CRT, that is the cathode ray tube. So let's start by defining what we mean by cathode rays. So cathode rays are simply fast moving electrons emitted from the cathode moving to the anode in a cathode ray tube. So it is important to note that the cathode rays are usually negatively charged because we are talking of electrons. Remember, electrons are simply negatively charged ions. Then, why are they always moving towards the anode? Remember, the anode is usually positively charged, and we said in the law, that is the basic law of charges, we said that unlike charges will always attract each other. So because the anode is positively charged and the electrons are usually negatively charged, that is why the electrons will always be attracted to the anode. Hence, the electrons are emitted from the cathode, then they are always moving towards the anode because the anode is positively charged. Therefore, it is going to attract the electrons which are negatively charged. Then, of course, in a cathode ray tube. So this is what we are calling a cathode ray tube. It has some features. We have the heating element. Then, of course, we have the anode, which is positively charged. We have the fluorescent screen, which will always glow whenever the electrons hit it. Then, of course, the tube is usually a vacuum, or we say it is evacuated. That is, we remove all the air from that particular tube. So let's look at the process of production of the cathode rays in a cathode ray tube. So cathode rays are produced in a cathode ray tube by a process called thermionic emission. So the word thermionic is from two terms. That is thermal, which simply means heat, then ion, which means either a positively or negatively charged material. So remember, under ions, the two types of ions, we have the electrons and the protons. The protons are positively charged, while the electrons are negatively charged. But for this case, we are going to be specifically concerned with the electrons, which are negatively charged, because we are saying that cathode rays are usually negatively charged. Therefore, when we talk of thermionic emission, we are simply talking of ions being produced as a result of heat, because thermal means heat, then ion means we are talking of the electrons. So we are simply talking of the electrons being produced as a result of heat. So that is what we are calling thermionic emission. So what is thermionic emission? Therefore, thermionic emission simply refers to the process of emission of electrons due to heat energy. So the filament heats up the cathode. So you can see we have our heater here, which has its filament. So the heater hits that particular filament. Then the filament is usually connected on the cathode. Then remember, cathode is usually negatively charged. Therefore, the filament heats up the cathode. Therefore, the electrons on the surface are going to gain kinetic energy, hence breaking away. So remember, the cathode, when it's heated, it has some electrons. Therefore, those electrons are going to gain kinetic energy. Remember, kinetic energy is the energy in motion, or it enables substances to move. So once these electrons are produced, then remember, this is a cathode, and the electrons are negatively charged, the cathode is also negatively charged, there is going to be repulsion. So because the electrons are negatively charged, they are going to repel the cathode. Then once they repel the cathode, there is a strong attraction from the anode here. Remember, the anode is usually positively charged, and unlike charges, will always attract each other. So when the electrons have been repelled by the cathode, they are going to be attracted by this particular anode, because unlike charges attract each other. So that attraction will accelerate the electrons, or will cause the electrons to move at a faster speed or velocity because of that particular attraction. So the filament heats up the cathode. The electrons on the surface gain kinetic energy, breaking away from the surface because they are repelled by this cathode, which is also negatively charged, because like charges will always repel each other. Then once they are repelled by the cathode, they are going to be attracted by the anode, because unlike charges will always attract each other. So once they are attracted by the anode, they'll be accelerated towards the fluorescent screen, which of course the fluorescent material will actually glow when those electrons hit the screen. So these electrons are then accelerated towards the fluorescent screen by the anode. So because of the attraction, that is what will cause these electrons to be accelerated towards the screen. Then when these electrons hit the fluorescent screen, the screen is going to glow. So the screen will glow at this particular point. Then the tube is usually evacuated. To evacuate is simply to remove the air, or simply to create a vacuum. So you can see this is a vacuum, so we remove all the air. You can use a vacuum pump to remove the air from this particular, the cathode ray tube. Why is it that we need a vacuum inside here, or we need an evacuated tube? So the reason is that so as to prevent the electrons from losing their energy as a result of interacting with air particles. So remember, if there were air particles here, the electrons, when they'll be moving towards the fluorescent screen, they'll be interacting or colliding with those air particles. So those collisions will reduce the speed of the electrons, causing the electrons to lose some of their kinetic energy. Remember, collision will cause the cathode rays to lose some of their kinetic energy, and we don't want that energy to get lost, so that the quality of our cathode rays are actually strong. So the tube is evacuated, or we remove the air from the tube, or we create a vacuum in the tube so as to prevent the electrons from losing energy as a result of interacting or colliding with air particles before reaching the screen. So this is our extra heat tension. So this is heat at very high, that is a voltage of about 12 volts, which is going to ensure that the cathode is heated to the maximum temperatures possible, causing the electrons to gain kinetic energy, being accelerated or being attracted by the cathode, that is the anode. Then of course they'll move to the screen. Why is the tube evacuated? So as to prevent our electrons from losing their kinetic energy as a result of colliding or interacting with air molecules that will be in this particular tube. So when it is a vacuum, there is no air molecules, therefore the cathode rays are not going to collide with anything. Therefore, most of them are going to reach this particular fluorescent screen, forming a stream of cathode rays. Next, we look at the properties of cathode rays. The first property is that cathode rays travel in straight line, just like light. So the other way of stating the same point, you can say that cathode rays obey rectilinear propagation. Remember, rectilinear propagation of light was just a property of light, which suggested that light travels in a straight line. Then we were proving rectilinear propagation of light by formation of shadows. You remember that experiment whereby we are putting some 3 cardboards, then we make a hole at the middle of those cardboard, then we were displacing one of the cardboards, whereby the observation were that the candle could not be seen at the end of the 3rd cardboard, that is if we displaced one of the cardboard. So that was simply an evidence that light can only travel in a straight line, that is when there is formation of shadows. So similarly, for the case of cathode rays, we can only prove that they travel in a straight line when we have formation of shadows. So for this particular case, we are going to take our opaque material. In this case, we are using the Maltese cross. Then we place it in a CRT, that is the cathode ray tube. Then we are going to produce the cathode rays, of course, at the cathode, whereby they'll be accelerated by our anode towards the fluorescent screen. So once they reach on this Maltese cross, we are going to see a formation of a Maltese cross, that is the shadow of the Maltese cross on this particular fluorescent screen, proving that these particular cathode rays are traveling in a straight line. So the only evidence to show that cathode rays travel in a straight line is that cathode rays, they cast or they form shadow of any solid object placed on their path, as seen by the Maltese cross, whereby we are having a shadow of the Maltese cross on the fluorescent screen. The second property of cathode rays is that cathode rays are negatively charged, therefore they are deflected by both electric and magnetic field. Remember, we said that cathode rays are basically electrons which are being accelerated by the anode towards the screen, and we know that electrons are negatively charged. That is from electrostatics 1, which is a chapter that we covered in this particular channel. So cathode rays are negatively charged. That is why they are able to be deflected by both electric and magnetic field. Remember, electric and magnetic field, there can only be deflection in those fields if a substance is charged, whether it is positively or negatively charged. Otherwise, if it doesn't have any charge, then we don't expect any deflection in those magnetic or electric field. So let's start by looking at electric field. So in the electric field, the cathode rays are deflected towards the positive plate. The reason being is that, remember, the positive plate is it is positively charged. Then we said that unlike charges will always attract each other. So we are having cathode rays here, which of course are negatively charged. So this is the cathode terminal. So the cathode rays are being produced. So because cathode rays are simply electrons, or they are negatively charged, they are going to be attracted towards the positive plate, or the positive terminal of that particular whatever material. So you can see the deflection of the cathode ray is towards this particular positively charged plate. Then of course it is being repelled from the negatively charged plates, hence the deflection is downwards towards the positively charged plate. Then we look at the direction of deflection in the magnetic field, whereby we are saying that the deflection, the direction of deflection in the magnetic field can be determined or predicted using the Fleming's left-hand rule. We looked at this particular rule. That is when we were looking with when we were dealing with the magnetic effect of the electric current. Also, that is the magnetic effect of the electric current, which was a chapter in Form 2. We also reviewed the same under electromagnetic induction. So you can just review, you see what we meant by the Fleming's left-hand rule. But basically it stated that if you hold the fingers of your left hand, that is such that the first finger points towards the direction of magnetic field, the second finger points in the direction of the current, then the thumb must always point in the direction of the motion, which will be the direction of the deflection of our cathode rays. Only that for this case, the second finger pointing in the opposite direction of the one of that is the second finger pointing in the opposite direction to the one the cathode rays are moving. Why should the second finger be pointing in the opposite direction? Remember, the second finger in our normal cases was pointing in the direction of the current. Then remember, current will always flow in a direction opposite to the direction of electrons. And because like for this case, this is the direction of motion of our cathode rays. And remember, cathode rays are simply electrons. So if electrons are moving from the left towards the right hand direction, then it simply means that current will be flowing from the right direction towards the left hand direction. That is why we are negating, we are letting the second finger to point in a direction opposite to the direction of the cathode rays, because cathode rays move, or electrons move, in a direction which is opposite to the direction of the current. Then remember, the second finger will always point in the direction of the current. So if the electrons are moving towards the right, then the current must be moving towards the left. So that is just by convection. Then we also stated that when we were dealing with the cells and simple circuits, which was the last chapter under Form 1 work, which we covered in this particular channel. You can also review. So you'll simply hold your left hand, of course, with the thumb, the first finger and the second finger being mutually at right angles or perpendicular to each other. Then you let the first finger to point in the direction of the magnetic field. You can see this the North Pole, this the South Pole. So the magnetic field will always move from the North Pole towards the South Pole. So that is why my first finger is pointing towards the screen or into the paper. Then the second finger must point in the direction opposite to the direction of the cathode rays, which is the direction of the current. So you can see the second finger is pointing to the left because the cathode rays are moving towards the right. So the second finger is pointing in the direction of the current. Therefore, if you observe your thumb, you will see that the thumb is pointing downward. That is why the deflection of the cathode rays is downward. So you can just use the second, that is the left hand, the Fleming's left hand rule, only to remember that the second finger should point in a direction opposite to the direction of the cathode. The reason being, the cathode travels in a direction opposite to the direction of the current, and the second finger is supposed to point in the direction of the current. So you can see that the deflection is downwards. That is where our motion or our thumb is pointing. So we can also denote those magnetic field using crosses and dots, which are encircled within that is a dot which is encircled. So remember, whenever you find crosses like this one, it means the magnetic fields are moving into the paper, or for this particular case, they are moving into the screen. So you will hold your first finger pointing towards the screen. Then, of course, the second finger has to point in a direction opposite to the direction of cathode rays. So the second finger has to point towards the left. Then, of course, you will realize that your thumb will be pointing downward. That is why you are seeing our cathode ray deflecting downward. Similarly, for this case, you can see the cathode ray is also deflecting downwards. Then whenever you see a dot which is encircled, then this one, it means the current, that is the magnetic field, is moving out of the paper or out of the screen. So in such cases, you will point your first finger towards yourself, that is out of the screen. Then the second finger in a direction reversing the direction of the cathode rays. Then the direction in which the thumb will be pointing, that is the direction of the cathode ray that will be deflecting. Lastly, we look at the third property of cathode rays, which states that cathode rays possess kinetic energy. So this one simply means that they can cause motion. So this can be ascertained by our diagram here, which is called the pedal wheel. So we have our pedal wheel here. We are just placing it along the path of the stream of cathode rays. So this is the cathode, which is going to produce our cathode rays. Then this is the anode, which will attract the cathode rays so as to accelerate them towards this particular anode. Then we are placing our pedal along the path of the stream of the cathode rays, which are being accelerated towards the anode. So it will be observed that when cathode rays are produced, this particular pedal wheel, it will start rotating, that is in the clockwise direction. So because the cathode rays that have been produced, they have kinetic energy, therefore they will cause this particular pedal wheel to rotate. So energy in motion, that is kinetic energy. So a pedal wheel placed on their path is therefore rotated. So this one simply shows that the cathode rays are able to cause motion. Therefore, they have what we call the kinetic energy, or simply the energy in motion. So the pedal wheel will start rotating in the clockwise direction, showing that the cathode rays can cause motion. The fourth property of cathode rays is that when cathode rays are stopped by a metallic target, X-rays are produced. So we shall discuss more about this one when we'll be looking at the X-rays, which is our next chapter. So remember, the process of producing X-rays simply involves producing cathode rays, then directing them towards a metal target. In most cases, we use the tungsten. Then when they are deflected from that particular target or the tungsten, then what you produce or what you obtain from the opposite side is what we call the X-rays. So this particular chapter will be very important in understanding our next chapter, which is the X-rays. Then the fifth property of cathode rays is that cathode rays are affected. That is, cathode rays affect photographic papers. When you direct them on the photographic papers, you are going to see an effect or a difference. So that is the other property, is that cathode rays affect photographic papers. Then the sixth and the last property of cathode rays is that cathode rays can ionize gas molecules through which they travel. They can ionize. That is the reason why we remove air molecules from the path of those particular cathode rays, so that we don't have any energy getting lost as a result of the cathode rays interacting with air molecules. To ionize is simply to charge. So they can charge air, of course, negatively because they are negatively charged. Then we look at the similarities between cathode rays and light. Of course, the first similarity is that they both travel in a straight line, or they obey rectilinear propagation. Then the second similarity is that they both affect photographic papers. That is why you can use light in taking photographs. Then the differences between cathode rays and light. The first difference is that cathode rays are charged, whereas light do not have any charge. So light cannot ionize any medium or molecules, but cathode rays have that ability because they are negatively charged. So they are able to charge materials or to ionize a given material, for example, air. Then the second difference between cathode rays and light is that cathode rays possess kinetic energy, whereas light do not possess kinetic energy. So light cannot cause motion, for example, of a pedal wheel, but for the case of cathode rays, they are able to cause motion. Then the last difference is that the direction of the current, that is, the direction of the current is in the opposite direction to that of the cathode rays. This is not the case for the light rays, because light rays in the first case, they do not have any charge. They are not charged. But for the case of cathode rays, the direction of the current is in the opposite direction to that of the cathode rays, because electrons and current, they always flow in opposite direction. So if electrons are flowing from the right hand direction towards the left hand direction, the current will flow from the left hand direction towards the right hand direction. So that is simply by convection. So we've come to the end of our class today, but we need to discuss the quote of the day. The quote of the day stated that you will never realize how strong you are until being strong is the only choice you have. So the quote is simply encouraging us to push ourselves to the limits of our potential. Each one of us was born with the ability and the potential to become anyone they want or they wish in their life. The only problem is that we have fear. Yeah, we are afraid of everything. We are afraid to try. We are afraid to take chances and to take opportunities. So we are afraid of what could go wrong if we tried doing something different, and that is what is holding us back. We are also afraid of what other people will say about us if our ideas do not work according to our original expectations. So lower your expectations, just do whatever you are doing. Do not put so much of your effort into what other people are saying, because not everyone is wishing the best for you. And lastly, remember that a lion does not concern himself with the opinions of the sheep. Therefore, do not allow anyone to instill fear in you. You are capable of becoming anyone you want. You just need to trust the process, believe in yourself, and more importantly, utilize the time that you have properly. So remember, we all have 24 hours in a day, but how you use that time is what creates the difference between the successful and those who are still yearning for success. Thank you very much for accompanying me until the end of this particular lesson. I do not take it for granted. In case you are new to the channel, kindly hit the subscription button and also turn on the notification bell so that whenever I upload a new video, you will get notified. Until next time, this is Kind Tuition Academy. Thank you very much.